Welcome to The Explainer. Today, we are going to break down one of the most fundamental structures in computer science, something that, believe it or not, is silently organizing a huge part of your digital life right now, the queue. So, here's how we're going to tackle this. First, we'll start with the super simple, real-world idea that everybody already understands. Then, we'll dig into the anatomy of a queue and the key things it can do. After that, and this is the really cool part, we'll look at two different ways to actually build one, using an array versus a linked list, and see why that choice is a huge deal. And finally, we'll wrap it all up with why this matters in the tech you use every single day. Okay, let's kick things off with a concept that is just completely intuitive. It's all about fairness. It's all about order. This right here, this analogy is everything. Seriously. If you can picture a line for movie tickets or for coffee, you already understand about 90% of what a queue is. It's that unwritten rule we all live by, first come, first served. Simple as that. So, in the programming world, we give this a fancy name, FIFO, which stands for first in, first out. It's not just a suggestion, it's a core guarantee. Whatever data goes into the system first is guaranteed to be the exact same data that gets processed first. No cutting in line allowed. All right. So now that we've got the main idea down, let's build on it. A queue isn't just a vague concept, it's a formal data structure. And that means it comes with its own specific lingo. So let's learn the key terms. First up, you've got the front, which some people also call the head. And it's exactly what it sounds like. This is the person at the very, very front of that ticket line, the next one up to be served. And of course, at the other end, we have the rear, or the tail. This is the end of the line. This is the spot where a new person joins in and starts waiting. Now, this is a really important distinction. We need to know two different things about our line's length. First is the size. That's simple. It's how many people are actually standing in line right this second. But then there's capacity, and that's the absolute maximum number of people the line can even hold. Think of it like a room with a fire code limit. The size can change, but the capacity is a fixed number we, as programmers, have to worry about. Okay, with the structure and the terms all laid out, let's talk about what a queue actually does. And really, it all boils down to two fundamental actions, putting things in and taking things out. The first action is called enqueue. It's just the official technical term for getting in line. So a new element, a new person, always goes to the rear of the queue. But wait, before we can add them, we have to ask, is the line already full? Is it at capacity? If it is, that's an error we call an overflow. But if there's room, boom, the new element is added to the back. And the opposite action, you guessed it, is dequeue. This is our person at the front finally getting their tickets. The element is removed from the front of the line. But again, there's a catch. What if the line is empty to begin with? Well, trying to serve someone who isn't there causes a different kind of error, one we call underflow. If the line's not empty, though, the front item is removed and the line gets one person shorter. Now, besides adding and removing, we have a few other handy operations that let us check on the queue without changing it. Think of peek as just taking a look at who's at the front of the line without actually serving them. Then we have isEmpty and isFull, which are simple yes or no questions. Is anyone in line? Is there any room left? And finally, size, which just tells us, hey, how many items are in here right now? These are all super important for managing the queue safely. Okay, so we know the rules of a queue. But how do we, actually build one in our code? This is where it gets really, really interesting. The first and most straightforward blueprint is something called an array. Just think of it as a fixed row of boxes, one after the other. So at first glance, an array seems perfect, right? To enqueue, you just add a new item to the next open spot at the end. It's super fast. But watch what happens when we dequeue. We take the first item out and now we have this awkward, empty space at the very front. To keep the line organized, we have no choice but to shift every single other element forward one spot to fill that gap. And that is a massive problem. This whole shifting business is what we call computationally expensive. We measure this cost with something called Big O notation. And for this operation, it's ON. Now, what does that mean? It just means the time it takes to do the job is directly tied to N, the number of items in the queue. So if you have 10 items, you do 10 shifts. But if you have 1,000,000 items, you have to do 1,000,000 shifts every single time. You can see how that just doesn't work for large-scale applications. So, if the simple array has this huge, glaring flaw, what's the alternative? Well, let's explore a much smarter, much more flexible approach, the linked list. So what on earth is a linked list? Well, instead of a rigid block of boxes, I want you to imagine a chain. Each link in the chain holds an item, and it also has a little pointer that just says, the next person in line is that one over there. Now, look how beautifully this solves our problem. To dequeue, we don't move a million people, we do one tiny thing. We just change that main front pointer to point to the second element in the chain instead of the first. And that's it. The first element is instantly gone from the line. It's brilliant, no shifting at all. And the result of that brilliant little move? The time complexity for dequeue plummets to O of 1, which we call constant time. This is a game changer. It means the operation takes the same teensy tiny amount of time, whether there are 10 items in the queue or 10 million. It is incredibly, incredibly efficient. So let's just put them head to head. Look at this. For adding items and peeking at the front, they're both O of 1. They're both super fast. But that middle row, the dequeue operation, that tells the entire story. The arrays O and N is a potential disaster waiting to happen. The linked list's O of 1 is always fast, always reliable. This one difference is exactly why the linked list is almost always the better choice for building a queue. So after all that, what's the big picture? What's the one thing you should really walk away with today? Here it is. The most important takeaway. A queue is just an abstract idea. It's a set of rules, like first in, first out. But as we just saw, how you choose to build it, the blueprint, the implementation, has massive real-world consequences. That choice between an array that grinds to a halt and a linked list that stays lightning fast can literally be the difference between an app that people love and one that they delete in frustration. And I promise you, this isn't just some abstract theory. Queues are the silent, unsung heroes of our digital world. That list of documents you sent to the printer, that's a queue. The emails sitting in your outbox waiting to send, that's a queue. The very data for the video you're streaming right now is being fed to your device from a buffer, which is, you guessed it, a queue. They are absolutely everywhere, just quietly ensuring fairness and order in a world of digital chaos. So the next time you see a little loading spinner on your screen, you'll know exactly what's going on. You're just watching something take its proper turn in an invisible digital line.